This is Unit 5D. It deals with Newton's third law and some of the consequences of it in terms of gas pressure and also momentum. So to begin with, here we have a familiar situation, or at least one we can relate to. We're in a boat, we want to move to the left, we haven't got an oar or a motor, and we can achieve this movement by throwing something in the opposite direction. So we've got our cannonball here. The double-headed arrow shows the force. We let it linger a bit longer. Obviously the force only is able to cause the interaction when there's actually contact. The ball goes that way, we go the other way. Now over here we have a less familiar but an actually more simple situation. The astronaut is trying to get back to his ship and he's got a hammer. He throws the hammer this direction and he moves in the opposite direction. So Newton 3 tells us the force must be the same, but the acceleration doesn't have to be. Because his mass is greater, his acceleration is smaller. Either way, it achieves the result of accelerating him back to where he wants to go. Now rockets use exactly the same principle. They don't throw hammers or cannonballs, they throw gas out the back. And so we have some kind of combustion process, force equal and opposite, and it pushes the gas out the back, pushes the spacecraft in the other direction. So to every action there is an equal and opposite reaction of the same type. We can also describe this in terms of momentum, so same force and must also be the same time. Now the momentum exchange must be the same, but the end velocity doesn't have to be, because again m can be different. Now here we have another situation of equal and opposite reactions again, and this time it's gravitational force we're interested in. So here we have a very everyday situation, someone jumping off a ledge or a chair and heading towards the ground. Now these two black equal and opposite arrows represent gravitational force, and again we see that there's no reason for acceleration to be the same. So a typical person might weigh 70 or 80 kilograms. The force is equal and opposite, but the acceleration won't be, because the mass of the Earth is very much greater than the human being. So here we have 10 to the 24, so 5.9 times a million, 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 million. Now let's see what happens when we allow the film to run and the person comes into contact with the ground. Well, what happens is we get an electrostatic pair being created. As soon as there's contact, the electrostatic force comes into play. So let's just run that and see what happens. So here we go, the person is attracted and accelerated downwards, the Earth is accelerated upwards but much less. There, when we have contact, we see the equal and opposite red forces there, and initially we saw that they spiked. They were very much bigger than the gravitational force, which makes sense, because otherwise we'd have no deceleration. So the object, the human being, has to decelerate. But now, a little while later, we see that that's all settled down, and we see a little bit of a reaction there. It's being compressed effectively, the ground. So the atoms getting closer together, and that's what generates our electrostatic pair there. Now, it just happens to be the case that this one here and this one here are equal and opposite, but that does not mean they are Newton 3 pairs, because they are not of the same type. The other pair is there. It's much harder to visualize and think about, and it's a very, very common mistake, but there are two pairs here, gravitational pair and the electrostatic pair. They just happen to be equal and opposite in this unusual situation once everything has stopped moving. Now here we have the graph of acceleration to try and visualize it in a different way. So to begin with, we have gravity accelerating the person downwards at a steady minus, indicating direction downwards, meters per second per second. As soon as we get the electrostatic force coming into play there, we have this very fast deceleration, and then after a while the forces balance again and we get no acceleration. Last situation then is more explicitly about momentum. So at the top here we have a collision. We have an object here and it gets hit by the blue one and they combine. Now if you look carefully you can see that the blue one slows down and the red one speeds up. Now it all seems very complicated, but the time of interaction must be the same, and as we know, the force must be equal and opposite. And we know that change in momentum is due to force times time. So whatever momentum one is losing, the other must be gaining. Therefore, total momentum must stay the same. And our little graph shows this. So if they have the same mass, blue momentum is more than red momentum, but the total is the same. They happen to end up at the same velocity in this case. It could have bounced up, but a simple case, same momentum. They each has the same momentum. In the situation here, we have the recoil of a rifle. So it's an explosion type situation, but the rifle has mass, it has velocity, the bullet has mass and velocity, so we can do the calculation. So beforehand, this is my way of showing 0. Nothing's moving, nothing has any velocity, so the total momentum is 0. Afterwards, we can see that the heavy rifle is moving to the left, and the fast but relatively light bullet is moving to the right. But again, we know they must be equal and opposite in momentum because they experience the same force for the same amount of time, just opposite. And we can see that here. And this also reinforces the idea that momentum is a vector because we can give it a plus and a minus value. So momentum changes occur in very small bits of matter as well as larger macroscopic objects. So here we're thinking about air particles or any other gas particle. Now what we're interested in is ultimately the relationship between temperature and also volume and what effect these two factors have way over here on pressure. We'll come back to the flowchart at the bottom. Let's look at some animations first. So here, to simplify things, we consider one particle which is moving around, so it has temperature. That's what temperature is, energy per particle, kinetic energy, and it's bouncing up and down in our container here at a constant speed. So the temperature is constant. Now this one here we can see is going at the same speed, so it has the same temperature. But here the volume, as indicated by V, it's always capital V, but this is a smaller capital V, is less, and so it has twice as many collisions for the same amount of time. Now more collisions is going to lead, here we can see, so less volume, it's going to be more collisions. More collisions means there's going to be, for any given period of time, there's going to be more momentum change, and momentum change requires force, and that force is coming from the container. While it's going both ways, as we know, forces always occur in pairs, and because the area we're considering, one side, is constant, that gives us more pressure. Now we can see that on a more complex scale here. We've got lots of particles bouncing around in all sorts of directions, but again, if we have less volume, there are going to be more collisions, therefore more pressure. Now over here we have the same volume, but now we have more temperature, or higher temperature. Again, we start simple with just one particle. It has the same distance to cover, but it's moving faster. That's what higher temperature means. So there are going to be more collisions, and also each one of those collisions is going to be harder, or is going to involve more force or a greater momentum change. So more and harder collisions, again more momentum change, more force required, and because the area stays constant, more pressure. And again, finally, we can see the same idea, but here with many particles. It's exactly the same principle, it's just happening in a more multifaceted, more multidimensional way.